And Linus, please take it away.
Should probably unmute myself before I say anything. Thank you guys. Thank you for having me. It's a pleasure to talk about this work, and it's really nice to have a seminar series of any kind, to be honest. So I'm very grateful that this exists and that I get to be part of this. I'm just going to share my screen, and then we tried this yesterday and it worked perfectly, so I'm very confident that it's going to work today as well, but I guess this is technology, so anything can happen. Yeah. And then I hope you can all see my screen and you can all see me right. Is that right? Yes, fantastic. Okay, thank you. So what I would like to talk about today is a particular problem, a particular framework of problems, really, that is not necessarily topological or geometrical in nature, but it is certainly interesting. And the particular application that we've been working on is topological in nature. So I hope I'm finding an audience that will find this interesting. And the main premise of the question is, so suppose you have some object. If it doesn't satisfy a particular property, it doesn't satisfy, a property, by how much does it fail? Does it fail? So this is a problem that is the general framework of this, which I will get into in a second, is due to Ulam. It's a problem from the 1960s, and it's called the Ulam stability problem, or Ulam stability questions, or just stability questions. And in general, you can think about this as a kind of, well, stability problem, of course, but in the most general sense, think about a theorem of any kind, really. I think in the slides I wrote, pick a theorem of your choice. I'm not sure whether you should really pick a theorem of your choice, but think about a theorem and wonder what happens if I change the hypotheses of the theorem. So if I weaken them, or if I take them away, or if I don't ensure that all of them are satisfied, what happens to the conclusion? Is the conclusion still a little bit true, or is it still almost true? And this can be applied to various kinds of questions. One of the original settings of this problem is in mechanics. So if you want to solve a particular differential equation, you wonder, if I find the solution, how much does it depend on the initial values, for instance? The particular question that I'll be looking at today is about homomorphisms. So, e.g., there's a nice theorem which says that if f from the reals to the reals, this is the additive group of reals, is a homomorphism, then it's continuous. And not only that, it's of the form f of x equals r times x for some r. And this is true whenever this is Borel. Okay, so this is a very nice characterization. It's pretty strong, especially because these groups, as additive groups, are Polish groups, which give us a lot of tools about topological continuity in general. So we get what is called automatic continuity for Polish groups, which are groups that are whose underlying topology is Polish. And this is something I'll talk about in a second as well, but I won't get too much into detail. So the point here is we have a strong theorem about something, about some kind of homomorphism, really.
Just a quick question, sorry.
Yes.
Can you remind me of the definition of a Borel homomorphism?
Yes, I can. So, so you have a topological space. Take the Borel sigma algebra. Oops. And thank you for asking, by the way. I meant to emphasize this. If any of you have any questions, please let me know. I've tried to build this talk from the ground up. So if there are any questions at any point, just let me know. So it's the Borel sigma algebra, which is made up of the open sets. So algebra generated by the open sets. Generated by the open sets of X. So you can define this Borel algebra on any topological space. And it's a sigma algebra, so it's closed under intersections, it's closed under finite intersections, finite unions, and complements, but it's sigma, so it's also closed under countable intersections and countable unions and complements. So every Borel set you can build it from countable intersections, countable unions, and complements. And what's important about the Borel hierarchy in general is that it is a hierarchy, so it can be stratified. You can, for any Borel set, determine where exactly it appears in the hierarchy. And in that sense, we talk about Borel sets and Borel functions as being definable. And that's something that plays a big role in subjects like descriptive set theory or in the general world of Borel equivalence relations. On a side note, you can use this classification to classify all kinds of mathematical problems in general by saying, okay, if I know how to solve this problem, is there a Borel isomorphism to another problem that I know how to solve anyway? It's similar to, if any of you know, computability theory, where I have a problem and then I have another problem and I can reduce one to the other using a machine. So in here, in this sense, the machine is the Borel isomorphism. But that's just a side note. Does that answer your question?
So I understand the Borel sigma algebra, but what is a Borel homomorphism then? Is it
yeah,
Borel
so
measurable? Or?
Yes. It means the preimage of every Borel set is Borel.
Okay, yeah, cool. Thanks.
Okay. So now I don't have such a strong assumption anymore. I don't want F to be a homomorphism. I just want F to be an almost homomorphism. So what if F satisfies that f of x plus y minus f of x minus f of y is in G for some countable group G? So in this sense now, I don't talk about homomorphisms anymore. I don't expect this to be equal to 0. Excuse me. I just want to know how much can I say how close is this to a homomorphism, and maybe these functions are relatively close to homomorphism. If their image or if that particular difference, this one always lies in G, then this is a reasonable notion of being close to homomorphism. And you can prove that if F is Borel at the same time, then this is a theorem by Kanovai and Reken. It's from 2000. It says that if F is such that, so if F is Borel, and this up here, this identity holds, then what is also true is that there is a Borel homomorphism, G, such that f of x minus g of x is in G. And because it's Borel, that means it's actually continuous. Again, by this automatic continuity property. So the point of this is, I have an approximation. This thing, I have an approximation. It's almost a homomorphism. What I can find is I can find a real homomorphism that approximates the thing I have very closely. And whatever we mean close or by approximate, that depends on the context. But this is the general idea. And I think that's worth writing down. So the general idea is, can any almost homomorphism be approximated by a real homomorphism or a strict homomorphism or any other kind of notion of homomorphism you like. And you can define this problem on any class of structures that allows for homomorphisms, almost homomorphisms, and a way of measuring whether something is close to an almost homomorphism. And it turns out that you can do this on many spaces. You can do this in many different contexts. So you can do this, for example, on C-star algebras, Boolean algebras, groups, of course, which is what I'll be talking about. In particular, Polish groups. So a Polish space or Polish group, a Polish space is a separable, completely metrizable space. So think of the real numbers, think of Cantor space, those kinds of spaces. Because we can exactly do what I mentioned just a minute ago. We can use all the facts of this classification of Borel sets. We have a Polish space. Because we can use what is really one of the main areas of descriptive set theory. So that's the general outline. Does that make sense so far? Are there any questions? So the general idea is I have some notion of homomorphism, I have some notion of almost homomorphism, and I want to know, can I measure how close they are to each other? Okay. And the particular framework which I'm going to talk about today is groups. And to do so and to motivate this, I'll say a few things about groups. So these things might be known to many of you already, but I think it's helpful to see why this is interesting. So this is about finite groups. As it turns out, if you want to answer more questions about these almost homomorphisms, especially when you talk about the real numbers, because of some topological properties of the reals, like connectedness, for example, you invariably also get to talk about group extensions. It's kind of a byproduct of solving the homomorphism problem. And that's what I'm going to outline now. So when you think of finite groups and of group theory in general, then there are some major problems that people wonder about. And one of them is, of course, the classification of groups. So classification of finite groups, let's say. And we know if we do this, the only thing we really need to worry about are the finite simple groups. So the simple groups are those which have no non-trivial normal subgroups. So if you can classify all finite simple groups, you can actually classify all finite groups. And that is because every finite group is built up from the finite simple groups. Every finite group is constructed, if you will, from simple groups. And it's really this construction that makes things difficult, because it's a very non-trivial way of constructing things. So if you've seen group extensions before, then you know that there's, for example, no unified theory to find all group extensions. And the problem for finding group extensions is usually how exactly do these groups interact with each other, the two you're using to build the group you want to build. And it's a hard problem. It's a very hard problem. And there's no unified theory that covers all cases. There's some. There's the Schreier approach from 1899 or 1899, I think, where he classifies all extensions, but he classifies them by the multiplication table. And that's not very useful, because how do you check whether two multiplication tables give you the same group? That's not easy to do. So it's not particularly useful. And I should, by the way, say that even if we could do this effectively, this classification of groups is not very useful, because there are many, many, many groups, and especially many, many, many finite groups, and big ones too. So it's not terribly useful, but it is intellectually useful. So I guess that's why people work so hard on the classification of finite simple groups anyway. Then again, I'm not a good theorist, so I hope I didn't do any. I hope I'm doing this justice. Let me put it that way. And the reason why classifying the groups is so hard is it is relatively easy to take one group and get its what I call the composition factors, but it's hard to use the composition factors to get the original group back. And I'll just give you an example of this. So if G is a finite group, we can write G is equal to n, which is a normal subgroup, which has this normal subgroup en minus 1 up to E0, which is the trivial group. So you look at your group and you take the maximal normal subgroups. So these are maximal normal. And you get a series like this. And what is special is because these are maximal normal, you get that EK plus 1, let's say, mod EK, this is always simple. Okay. So this is exactly the decomposition. You can take a group and you can decompose it into its composition factors. Oops. And these are composition factors, so these are all simple, if and only if I pick the maximal normal subset. Think of rings with unity and taking a maximal idea. It's a field if and only if I take the maximal idea. This is kind of the same argument. I mean, the proof is not really the same, but intuitively it's the same, it's a similar idea, let's say. And this is useful in many other cases anyway. I'll just give you an example very quickly. So I take Z4, by the way, if I write this, if I write ZK, I mean Z mod KZ. I'm not talking about p-adix or anything similar. So Z4, for example, is a normal subgroup, something of order 2, just Z2, and that's trivial. So that's all. There's nothing else in there. I can look at S4, which is a symmetric group on 4 elements, which has a normal subgroup A4, which has Z2 times Z2, which has a normal subgroup of order 2, which again is simple. So it has a trivial decomposition series. And another one that is relatively famous is S5, A5, which is of course simple. And this is, let's say, famous because it features in Galois theory, because this is not solvable. So this is exactly the argument using the Galois correspondence why there's no solution for quintic polynomials. So if you've seen Galois theory before, then that's why this is interesting. But that's just an aside. So. The other convention that I'm using is when I write things such as Z2 times Z2 is a normal subgroup of A4, that's of course not quite true. A4 does not contain Z2 times Z2, but it does contain a group that is isomorphic to Z2 times Z2. So just so that I've said it once, this is what I'm doing. And now the other direction is much harder. So for example, suppose you have something like E2, E1, and then E0, which is the trivial group. And you know the composition factors are Z3 and Z2. And I want to know what is G, or I'm asking what could G be possibly? What options are there for G? So I work from right to left, and I start by looking at these two. So I know that E1 modulo E0 is isomorphic to, which one is it? I'm using this one, so Z3. Well, E0 is the trivial group, so this is just E1. And this tells me already that E1 is the cyclic group of 3 elements. So I'm done. That's easy. And that makes sense. Simple groups have a trivial decomposition series, so I wouldn't expect anything crazy here. Because this is abelian, it has to be a cyclic group of prime order. So it has to be to be Z3 in this case. But now the next step, that's the one that's a little tricky. So here we have E2 modulo E1 is isomorphic to Z2. Okay, and I know that E1 is Z3. So that tells me that E2 modulo Z3 is isomorphic to Z2. And it's not quite clear what E2 is now. It's not obvious. It's not something I can read off. I need to think a little bit what it could be. And what I realize is, okay, this has order 3, this has order 2, so E2 must have order 6. And now I ask, how many groups are there of order 6? And there are only 2. So this is either S3 or it's Z6, which is the same as Z2 times Z3. Has to be one of those two. But what I also require is that it has to contain a normal subgroup of order 3, right? Which both of these do. So G is either of those two. This is not trivial, especially at this stage now. Imagine we had more terms in this direction. Imagine this sequence didn't only have 2 non-trivial terms, so not only those 2, but 5 or 6 or 7. It gets pretty tricky pretty quickly to see what the extensions should be. Like, how do we recover the group we started with? So it's a hard problem. And that's one reason why it is hard in general. Okay. This is just motivation, so it doesn't actually feature in the actual arguments of what I'm talking about, but it gives some intuition as to why this is hard in general. But it also gives us a natural way of thinking about extensions. So this is where the extension part comes from. We can now define. We say E2, just this one. E2 is an extension of E2 mod E1 by E1. And the sequence was, I'll just write it down again, it was E2, which was the group G, which contains E1, which contains E0, which is trivial. Don't try to make sense too much of this definition, in the sense that it says E2 extends the quotient by E1. It's pretty terrible notation, and it's not universally agreed on. If you read any book on group extensions or any article on group extensions or any paragraph on group extensions, make sure you know beforehand what convention people use, because some people use different convention and they say E2 is an extension of E1 by E2 mod E1. I've seen it both ways, and there doesn't seem to be any consensus as to which is the right one. So just be warned if you see anything about group extensions ever again. Now, if you see this, you can also see that, for example, if n is a normal subgroup of G, then G is an extension of G mod n by n. Right. And this is the canonical example. And we'll usually use a different definition for group extensions, which is equivalent though. Which I won't show you this, but you can kind of see why it should be. If you think of short exact sequences, then this is the same as saying you have groups of this form. So equivalently, when this is an injection and this is a surjection, surjection, and the image of I is equal to the kernel. That's the definition of a short exact sequence. If you haven't seen this before, it's not terribly relevant. Just let me tell you that it is very useful to use when we talk about group extensions. It's much nicer to talk about than about actual groups as we did here. Like this kind of stuff is fine, but talking about short exact sequences gives us a lot more structure, especially when all groups involved are abelian, which they will be. So it's a little nicer to work with. And from this, you can see, by the way, that this is in G mod n. Also, yeah, that this is a group extension, where this is the canonical injection, and this is the canonical quotient. Okay, so group extensions. Many questions about them, mainly about how do we classify group extensions. You know, I might be able to give two, as I did up here, where I said we have extensions S3 and Z6, but I haven't really classified them in any meaningful way. I just kind of did trial and error, and then I did some ad hoc reasoning. That's how I found them. Can we classify them in some other ways? And using short exact sequences, in fact, you can. I would just say a couple of things about them, just so you know. From now on, assume A and H are abelian, because it makes things infinitely nicer. And later, we will just look at abelian extensions. So in those cases, E would be abelian as well, but not yet. So firstly,
sorry, Linus, there was a question in the chat, but I think you've kind of answered it. So A doesn't have to be abelian always. That's just a nicer case.
That is correct. Yes, it does not have to be. You can define group extensions on all kinds of groups, and it's just that the theory that you use to find them or to classify them, it just gets harder and harder. So working in this abelian context is nice because it gives rise to group cohomology, which I will get to in a second. I hope that answers the question. So assume these are abelian. Question, is E always abelian? No, it's not. We already proved that just now, and we said, no, this was Z3 and this was Z2, I believe. So and we had S3 in the middle. That's not abelian. What if we have two, are all extensions isomorphic? Well, no, they can't be, because I just said we have, you know, there's an abelian one, there's a non-abelian one. If two extensions are isomorphic, are they kind of the same? And that's an interesting question. So suppose you have an extension A, and then you have two more like this. So I sometimes switch between 0 and 1. It's the same thing, and just mixing up additive and multiplicative notation. So it doesn't change anything. If you can find a map here so that this diagram commutes, so this commutes, then E1 and E2 are equivalent extensions. Okay. And in that case, of course, they are also isomorphic. So then E1 is isomorphic to E2. And the natural question now is, if E1 and E2 are isomorphic, does that mean they give you the same kind of extension? And the answer is no. So you can have distinct extensions, even though the middle groups are isomorphic, which I should probably say. So you can have distinct extensions with isomorphic middle groups. So basically, anything you would hope for these extensions to be true to make them nice, they're not true. You can't really infer much from one extension from another, but generally, this is exactly what I mean. These kinds of things.
No, that's fine. I'm just wondering, So these are isomorphic. What do you mean by distinct extensions then?
Yeah, so that's a good question. What you can have is you can have E1 and E2 to be homomorphic. Exactly. Yes. Construct this very easily by picking Z, to use a different color, by picking was it Z3 here and Z9 here and Z3 here. And then you have here a map that sends 1 to 3, and here you have one that sends 1 to 6. And if you do this, so this one's also Z9. If you do the usual quality, one of the normal subgroups maps everything to 1, it maps everything to 2. So that doesn't work. Yeah, but that's a good one. Thank you for mentioning that. Okay. So there's a nice thing about if everything is abelian. Everything is abelian, then we can use cocycles. Which are functions that take pairs of elements of A and map them to H. And they satisfy a few properties, so they're abelian cocycles. Say that where C of x, y is equal to C of y, x. And you have that C of x, y plus C of x plus y, z is equal to C of x plus z. So x, z plus C of x plus z, y. Where this is called the cocycle condition. And it's the thing that makes things work, let's say. The point is, that's very important, regardless of what the technical piece of this particular function are. The point is, if I have a cocycle, such C gives me an extension of A by H. That's the important bit. And it even works the other way around. If I have an abelian extension, then that is actually constructed by a cocycle, which is nice. So this actually gives us a handle on all cocycles, on all extensions. If I want to look at all abelian extensions of abelian groups, I just need to look at all cocycles. And I need to classify them in some way. And I mean, topologists, geotopologists, they are cocycles, so they are boundaries, and I can just look at the quotient group, and then I know what is interesting, what isn't interesting. So a cocycle is a coboundary if C of x, y is actually equal to eta of x plus eta of y minus eta of x plus y. So in some sense, if a cocycle is measured, the way in which the cocycle fails to be a homomorphism can be measured in some nice way, then this is actually a simple thing to look at. And that's exactly when it's a coboundary. Okay. And now you can classify them. And you can look at the second, this would be A and H. You can look at the second cohomology group. And it exactly gives you the group extensions. Gives group extensions of A by H. So that's very nice. If everything's abelian, that is. So this is this part. Of A by H and vice versa, I should say. So if you have an extension, it's induced by some cocycle. Okay. And now the particular case that we looked at, which is already, so we're almost done now, is where you look at where these groups are Borel. So you look at Borel cocycles. Look at Borel cocycles. So now A and H are Polish groups, Polish spaces, and not Polish groups, whose group operation is Borel. And Polish means it's separable, so there's a countable dense subset, and it's completely metrizable. And this time you don't classify all cocycles, you only classify the Borel cocycles. So look at the Borel cocycles. So these are the ones that are now C from A to H is Borel, is a map. And again, that means that the pre-image of a Borel set is Borel. So it's Borel measurable. And this is basically the same argument, or it's the same result that I mentioned earlier when I mentioned the Canova and Reken result about approximating homomorphism approximations. It really is a result of this theorem, which is also by Canova and Reken from the same year. It's actually from the same paper, which says that this group 0. So if you look at all the Borel cocycles from the reals to some countable G is countable, some countable G, then this group is trivial. So every Borel cocycle is actually a Borel co-boundary. And that's exactly the key ingredient in the proof that every almost homomorphism from the reals to the reals can be so closely approximated by an actual homomorphism. So this is the result. And now let me just state that Lupini and myself, we extended this to show that this is true for all n. So this is also true if n is greater than 1. The proof has nothing to do with group extensions or anything, really. It just messes with cocycles. So you have these cocycles, which really, you can think of them, each one, you can think of it as a group extension. And the only thing you need to do is you need to show that each cocycle is actually a co-boundary. Because that's exactly what it is, because this is the quotient group, of course. So this is the Z, oops. So it's the Z, the cocycles over the boundaries. So if you show that every cocycle is a co-boundary, you're done. And you can do this by shifting things around. And you use the fact that the cocycle is Borel. So the main argument of the proof is that C is Borel. So it's sufficiently nice on some open interval. This follows from the bare category theorem, by the way. And what do I mean by nice? I mean, you can look at co-meager subsets. So think of a large subset of this open interval I. If you take any 2 points from this large subset, then C is actually constant. So that's very nice. And in a sense, it gives an indication as to why such a function should be easily approximable. If a function is constant on a very big set, then I should be able to find a nice function that kind of approximates it nicely. And that nice function can actually be a homomorphism itself. The remaining argument uses forcing results. So if any of you are familiar with forcing in set theory, for example, it exists in set theory and computability theory. there's a slide on the handout that Grace put in the chat as well. So if any of you are interested in it, you can take a look at that. I'll just say two things about it. The general idea is to build objects using approximations. And these approximations are ordered in a partially ordered set. And you look at all the dense open sets in this partially ordered set. And you want to make sure to meet as many as possible of these dense open sets. Think of each dense open set as some kind of condition. So if you meet enough of them, you can satisfy enough conditions. So you can force your object that you're building to satisfy certain things. Historically, this comes from someone called Paul Cohen. He invented this in 1963 to solve the continuum hypothesis, which is one, I think, Hilbert's first problem. But since then, it's been used in many other areas of maths, especially computability theory. And you can use it in topology as well when you think about co-omega sets. So sets that are complements of very, very small, negligible sets in a sense. The point in this kind of argument is that sets that are, oops, sorry, screen just, there we go. The point is that generic elements, so these elements that we are building from approximations, they're not special. They don't satisfy any special properties. So for instance, if I build a long string of 0 and 1s, it will not terminate in infinitely many zeros because there are dense open sets above any finite string that contains 1s. Basically, I can never miss such a point. I will always have another 1 in it. And in the same sense, that is exactly why C is nice on such an interval. And so for our proof, we basically emulated that argument. We had to take care of a few technicalities because this space is a bit bigger. It's R and it's not just R. So relating everything back to I is not as easy. You can't just take an open interval and copy it and cover the whole real line. That doesn't really work if you work in R2, for example. You have to kind of stretch it out into multiple dimensions, really. But otherwise, the argument very much relies on the connectedness of the real numbers, and those are still true in R2 and R3 and Rn. So it goes through. Yeah, so the main idea of all of this is really, if there's some notion of homomorphism, some notion of almost homomorphism, and some notion of measuring how close they are to each other, can I find a real homomorphism that approximates the old one? And in this particular case, the point is that if I look at group extensions, I can actually look at group extensions in terms of cocycles. And when I look at cocycles, I'm actually talking about almost homomorphism, if you will, because the co-boundaries are exactly those that kind of measure how much something fails to be a co-boundary. So obviously the co-boundaries generate the trivial extension. Any two cocycles that differ by a co-boundary are cohomologous. So this is the part that's missing here. C minus C prime equals C equals eta of x plus eta of y minus eta of x plus y implies C and C prime are cohomologous, right? So this is what you would expect really from cocycles and co-boundaries. So in that sense, it's almost a homomorphism, and it kind of wraps it all up and gives the general result. Yeah, if you have interest, take a look at the slides. This was not very technical talk, I hope, but more of a high-level argument. I didn't really go into any detail, but yeah, I hope you could take something away from it. Thank you for listening. Thanks for coming today.
Everyone, please join me in thanking the speaker. Do we have any questions? I have maybe a naive question, which was that a lot of this, or at least the end results, were done over R and for like spaces Rn. If we change that to some other kind of space, do you have any idea about what will happen?
So there's a few results. If you replace this by Cantor space and this by Cantor space, then this is not trivial. So that's a result. We were thinking about what happens if you look at the p-adix, for example, which obviously not connected. not easy. I don't know. It's the general question of, you know, where to go next. What happens if you don't have a countable group G? If this is not countable, then you can't really make use of the fact that the cocycle is nice, because it's the Borel condition on the countable set that gives you the nice interval in which everything's nice. So what happens if you don't have that? I don't know. You also don't need to think about groups. You can think about other structures, like as I said at the start, like C-star algebras or Boolean algebras. It's not clear.
Thank you.